which means All right, folks, not 2:05. It's I see 19 of you. I'm gonna begin. No, I think I said that we're gonna try and finish up digestive system today. I think we're 20 something slides in. Right, so we're just about here, stomach. Now we're gonna need to speak also about tomorrow because I'm being told that there are no labs in Kingston. So we're not gonna have labs tomorrow. However, we still do need to get the lab quiz out of the way. So I propose Sunday, 7 p.m. for the lab quiz. I'll ask again later, but basically that's where we are right now. Electrolytes, Sunday, 7 p.m. With that said, um, let's continue. All right, so the stomach has several functions. One of the main ones is going to be, of course, the chemical breakdown of proteins, as well as a small amount in terms of lipids as well, right? But mainly proteins. Now, the stomach is divided into specific regions. We have the cardiac region, the fundus, the body, and the pyloric region. So let's run through that first. Now, here we have the cardiac region. It sounds weird to call some part of the stomach cardiac, right? What about this? Looks like the heart. Nothing at all. But there's a structure in this region here called the cardiac sphincter. The cardiac sphincter, or the gastroesophageal sphincter, closes, we spoke about this last time, closes off the stomach from the esophagus. So what that means is that when food comes in the stomach, you have the sphincter muscle on either side here of the esophagus here, that squeeze is closed. And that stops the food, of course, from leaving, usually. All right. So that doesn't explain to you why it's called the cardiac sphincter. See, this makes sense to you. It's called a cardiac sphincter because of heartburn. Now, heartburn obviously does not come from your heart. I'm assuming everybody knows that part. But people used to believe heartburn was associated with the heart. Hence, heartburn. If you think about it, normally, where do you feel a burning sensation? In the chest. Okay. And because heartburn is actually caused by mixture of semi-digested food and gastric juice, which we call chyme, going back up into the esophagus because of the cardiac sphincter opening for whatever reason. And that would cause a common corona, and that would cause this acidic liquid to burn the esophagus. It would then get that burning sensation once again in the chest, so it would be called heartburn. Yes, Corona, what was the question?
Good afternoon, sir. Just a weird question. So when time pregnant mommies are saying that, oh, then just a burn them because the baby have up a ear pan head. A lie, right?
How does the baby get hair on the ear on in their head? That one, honestly, is the first time hearing that one. But there pretty much is no way that can happen. All right.
So then always say once the baby hair go enough, the mothers them always have a lot of ear and the babies them normally have a lot of ear on their head.
Yeah, that's not like some voodoo business. What I can tell you is this: when if let's say the baby is a larger baby or the mother is further down in her pregnancy, because of the position of the baby, the womb as it expands, is to press against the stomach. And because of that now, you're adding additional pressure to the stomach, which makes it easier for the cardiac sphincter to get forced open, to pop open due to the pressure. It's also one of the reasons why you'll find that when women are advanced in their pregnancy, they have a hard time eating a lot of food at any given time. They'll be eating continuously through the day, but they can't sit down and have like a big meal because it'll come right back up. All right. So this hair on the baby head, I cannot think of any logical reason why that would have anything to do with heartburn. But interesting idea. Never heard that one before. All right. So that is the cardiac region, right? First part of the stomach connected to your esophagus, called thus because of heartburn. Just the way the sphincter is called thus because of heartburn, right? Then now we come to the fundus. And it's the part that sticks up here. It is the most anterior part of the stomach. It's the highest part, right? There's the cardiac region down here and the fundus up here, right? So normally, of course, you're not going to have a lot of food up in the fundus unless you fill your stomach, right? Then now, the main part of the stomach is called the body, right? So the stomach has a body, which sounds weird. Go ahead, Zanel.
So just to clarify, you said that the cardiac region connects to the esophagus and it is what causes heartburn.
Because the chime is leaving the stomach at that region and going into the esophagus. That is where the heartburn comes from. Remember, you don't feel you feel a burning sensation in your chest. And it's in that's because that's where most of the esophagus is. Right?
So it's called the acid reflux.
Acid reflux, well, acid reflux is sort of a condition that it occurs regularly. If you just kind of vomit up a little bit, and that's just heartburn. But if it's happening to you multiple times, then it would be considered acid reflux disease. Now, that said, as I said, the body, main part here of the stomach, right? This is where a lot of the mixing up of the food with the stomach secretions or the gastric juice is going to happen. Okay. Now, further down from there, we have what is called the pyloric region. Right? You notice here we have pyloric antrum, which we'll talk about in a little bit, pyloric canals, and pyloric sphincters. Okay. This region here is where the food is, the chime is what we're going to call it now, which is a mixture of, as I said, the food and the gastric juices will sit for a little while. And then it will be squirted, literally squirted out of the stomach at intervals through the pyloric sphincter. And the sphincter leads right into the duodenum, which of course is the first part of the small intestine, right? So when you eat food, the food doesn't just go to the stomach and then passes out, right? Things happen to the food in the stomach, and then the food, and then once you make the chime, you pass it out little by little. So this, of course, happens during the course of several hours. For most people, if you eat a meal somewhere between 2 and 6 hours, it varies from person to person, your stomach will get empty again. Normally, we have meals at multiple times throughout the day, right? Because once our stomach is completely empty and your blood sugar starts to fall, of course, it triggers the hunger reflex, right? That said, you do have people who eat once a day, twice a day, but they eat like very large meals, right? I know one person that pretty much eats a gigantic breakfast and then they have like a small plate of fruit or something in the evening for them dinner, and that's it for them, right? Now the good thing about that is that once you've been doing something for a while in terms of eating patterns, your brain and your body will adjust to it. So what you'll find is that the people who are eating once a day, you ask them, say, you're not hungry, and they say no, That's because their body has gotten used to the rhythm of their eating habits. That's another thing. Eating habits are good, right? You can have good eating habits. But if you're eating randomly, whenever you can catch a minute, all kind of things, it does actually affect when you feel hunger, right? Because you're between your brain and your stomach, you're trying to figure out they're trying to figure out when food is supposed to be here. So if you eat breakfast this morning and then tomorrow you're not having a breakfast, and then the next day you skip dinner, your poor stomach between your stomach and your brain, you're not sure when there is supposed to be food, and you just find yourself feeling hungry at random periods. You don't know what's going on, right? Anyway, you'll also notice here that the stomach, very much like the kidney, has two curves, right? But remember, in the kidney, it was a lateral curve, concave, and a medial convex. Um, Lateral convex, sorry, medial concave. Here now, we call the curves of the stomach a greater curvature and a lesser curvature. The greater curvature, of course, is on the outside. Lesser curvature is on the inside, right? Now, that said, I want to point out these things here called the rugae. They look like little folds in the stomach. And that is because that is exactly what they are. They're folds of the stomach. This allows the stomach to stretch, right? And contain a fair amount of food. By that I mean, the average person can easily put 2 pounds of food in the stomach, right? Easily. Again, 2 pounds doesn't even sound like that much, does it? Right? But you can imagine somebody consuming the equivalent of breakfast, lunch, and dinner at one time. Your stomach can manage. It's not a big deal for your stomach, right? Um, One of the reasons for this is because human beings, along with most animals, evolved in, in an environment in which food availability was very random in most cases, right? You didn't know if you were to eat today or tomorrow. So when you came in contact with a lot of food, what do? You put as much of it in you as possible. So your ancestors would come across, maybe a tree that was fruiting, and they'd eat like 5 pounds of fruit. Why? Because tomorrow they might be going hungry, right? Or if they come across the carcass of a dead animal, everybody eat as much meat as they can, because tomorrow, who knows, right? So the rugae would have allowed the stretching of the stomach to accommodate times in which you consume much larger than normal portions of food, right? So for some of us now, so that is Christmas dinner. That is why during Christmas dinner, people are eating and eating and eating, same like they're packing away 10 times the amount of food they normally eat, you know? Because of course your stomach has space for it. The real rugae allows it to stretch to accommodate that excess food. And we'll talk about niggeritis later. Now, I also want you to notice that your stomach has 3 layers of muscle. Yes, go ahead, Tessini.
So sir, the rugae makes your stomach grow bigger, like when it
It
eats.
allows the stomach to stretch like a balloon. So it accommodates more things. There's a reason why when you eat a lot of food, you feel like your belly look big. Because your stomach is literally stretching to accommodate that extra food in there, right? All right. Now,
Sir, that's
yeah,
why they say people that have no belly button. If that's why they say why people that have no belly button.
the greedy people. It's not many people, greedy people that said have any belly button because in a lot of ways, you know, their stomach can stretch. So they eat and eat and eat and eat and eat, and their stomachs will stretch beyond this normal capacity or what you'd consider normal. Also, believe it
Sir,
or not, the more
sir.
often you consume large volumes of food, the more rugae develop and the more your stomach can stretch. Go ahead, Shemis.
Yeah, so I don't know if I'm me alone used to do this, but like us girls, like oh, wear I always pants and thing, and like when I will go out, go eat, and we start eat and realize, no, so this not gonna work.
Well,
We
if your stomach
unbutton the
can
pants,
stretch.
we unbutton the pants, sir, so
Yep.
the space. We
That
have
is
more space to eat.
that is very normal. Right? Once again, go back to Christmas dinner. When people eat, as a matter of fact, I know people who when it's Christmas time, they come they wear the loosest clothes they can because they know that it's roll if roll them out of the place, right? But yeah, if you are one of these who like the tight clothes, you can't wear tight clothes and go eat whole heap of food. You can't manage. The overeating, it's funny, you know, when it comes to nausea and overeating, is if you eat rapidly, you are more likely to feel nauseous because you're forcing your stomach to stretch too quickly, right? But if you sit down and just eat at a regular pace, you will find that you will consume a large amount of food, but you won't feel nauseous. But if you're trying to box away 3 days worth of food in 10 minutes, of course, you're going to feel nauseous. Anyway, 3 layers of muscle, right? We mentioned this last week at the lab. We have oblique muscle, which is the first layer this time, right? The first layer. And I want you to notice how the oblique fibers are running. So they go like this. So they're going at a less than 90-degree angle, right? Then, of course, circular muscle fibers go that way, right? And longitudinal muscle fibers, they actually go like this. That's the longitudinal ones, right? So what this means is that on the muscle fibers, when they contract, they're all causing contraction in a slightly different direction. Okay? This is important because when you have the food in the stomach and you need to do mechanical digestion, you do this by squeezing down on the food to help crush the food. So if you don't chew the food properly, when it gets to the stomach tries to do that for you, right? And as it is squashing down the food, and that is, remember, that is mechanical digestion, it is also mixing the food with the gastric juice, which contains acids and enzymes and all these things, and it's churning it up to make what we call chyme, as you know, right? So this is the reason why the stomach is the only part of the digestive tract which has 3 different muscle layers. Everybody else is only 2 layers of muscle, circular and longitudinal, right? Only the stomach has oblique. All right. Then, of course, on the outside, we have our serosa here, right? Now, that said, let's also talk now about the things that cover the stomach. So we have something called the omentum. We have a lesser omentum and a greater omentum. These are connective tissue layers that cover the stomach, right? As it says here, the lesser omentum runs from the liver to the lesser curvature, and the greater omentum drapes inferiorly from the greater curvature to the small intestine. All right, what are we talking about here? What we're saying is that there's a strip of tissue that is running, that is running from this part of the stomach, like this, and attaching the stomach to the liver, right? And that is your lesser omentum. You also have a big sheet of tissue that runs from the stomach and goes all the way down and covers the small intestine. And that is your greater omentum. So when you cut open an animal, you're dissecting the animal and you open up the abdominal cavity. There's a sheet of tissue you have to cut through before you see the intestines. That's what I'm talking about, right? And it's coming from the stomach. All right. Then now, stomach, nervous system briefly. We have sympathetic and parasympathetic innervations of the stomach, and they're coming, of course, from the autonomic nervous system. Now, you're also going to get blood going to the stomach from the celiac trunk, right? And of course, celiac veins are going to take blood away, right? And as mentioned, and the corresponding celiac vein is a part of the hepatic portal system. So what do you have happening? You have blood coming into the stomach from the celiac trunk and then leaving by the celiac vein and heading to the liver. We spoke about why blood from the intestines goes via hepatic portal veins to the liver first, right? So even blood from the stomach itself is also going to the liver first for the same reason, right? And there might be things in the food you're consuming that are not good, that may get into the blood supply from the liver, from the stomach. So you want to send that blood to the intestines before, sorry, to the kidney, the liver before you send it anywhere else. Now I'm hoping you realize that this suggests strongly that substances can be absorbed straight from your stomach and get into your blood. Okay? For example, this is how you get drunk normally. Alcohol can easily diffuse from your stomach and your intestines, of course, and move into your bloodstream from there, right? Now, this is good. Remember, alcohol is a poison. So what normally happens is that the alcohol goes to your liver first, and it is going to be normally there's an enzyme in there called hydrolase. It's some type of hydrolase enzyme. I think it's ethanoic hydrolase. I don't remember exactly. But the hydrolase enzyme breaks down the alcohol that is coming through, right? Which of course means you should not normally get alcohol going to the brain. The only way to do this is to overcome your liver's ability to produce hydrolase enzyme and therefore break down the alcohol, okay? So what happens is that normally you produce a small amount of the stuff, not very much. So the first time you go drinking, you easily overcome your liver's ability to make hydrolase, and you find that people who start drinking, they get drunk real fast, right? 3 beer and them up on a rum, kind of thing, right? But as you continue to drink, your body assumes that you're being poisoned regularly, and it produces more and more hydrolase. So your liver becomes more and more efficient at removing alcohol. Because remember, as much as you're trying to get drunk, your body is trying not to get poisoned. So the more you drink and the more often you drink, the more alcohol you'll need to get drunk because your liver is producing more and more of the enzyme to break down the alcohol. Okay? And remember, this is mostly coming from the alcohol being absorbed into your bloodstream at the stomach and then moving into your liver from there. All right. Now, let's now talk about the functions of the bits and pieces of the liver, the stomach. Right? Now, We already spoke about the oblique layers, right? So we don't need to go through that again. Epithelium. What is the liver's epithelium like? It mentions here goblet cells that produce a coat of alkaline mucus.
Sir,
Yes,
you keep saying liver.
I keep saying liver, don't I?
Yes.
Actually, I feel for some liver, and that's the problem. I've liver up on my mind from morning, I want some. Anyway, please remember, if you hear me say liver, I probably mean stomach. I'm trying to avoid thinking about liver, but it's like trying to avoid thinking of a pink elephant is getting to me. One more time. The muscularis of the stomach has an oblique layer. Some liver and fried dumpling be so nice right now. Moving on. This allows, of course, the churning, okay? Now, epithelial lining of the stomach, so it's stomach that time, it is going to be mainly simple columnar cells, okay? And one thing simple columnar cells tend to have with them is that they tend to have goblet cells. Goblet cells, of course, produce mucus. But the mucus that is being produced in the stomach, I almost said liver a little while ago, is very alkaline, right? It is very alkaline. Why is it alkaline? Remember your stomach is supposed to be the most acidic part of the body, right? Because you're literally producing hydrochloric acid. And as you all know from CSEC, the hydrochloric acid is there to do a couple of things. One, the stomach acid is strong enough to kill most bacteria. Most, certainly not all, but most. And two, the hydrochloric acid helps to activate protein digesting enzymes, right? So if you're trying to make the contents of your stomach acidic, why are you making alkaline mucus? That seems to be counter to what you're trying to do. Here's the thing. As much as the hydrochloric acid can kill bacteria, it can kill your own cells, right? The cells of the stomach are not somehow magically immune to the effect of hydrochloric acid. So what your stomach does is it produces the mucus to coat, to line itself, right? So the epithelial layer is covered in mucus. So even when the acid is out there doing its thing, there is a barrier between the acid and your stomach lining. When that barrier gets removed, that is how you get an ulcer, because the acid literally eats down into your stomach wall, okay? So that is why you need this very bicarbonate-rich mucus. Okay. Now, aside from goblet cells making all this alkaline mucus, what else do you have in the wall of your stomach? It mentions here you have gastric pits, and they contain gastric glands that are going to make the gastric juice. And I've mentioned gastric juice several times already. What is in the gastric juice? Enzymes, hormones, and of course, mucus. When it comes to the stomach, everything has mucus, right? This lovely diagram here, of course, I'm expecting you to know how to label, right? This is a section for your stomach. Last week, when we looked at the stomach for the digestive system, I mentioned to you that all segments of a digestive system have the same layers, which are, of course, mucosa, submucosa, your muscularis externa or muscularis propria, and then you have a serosa, right? And what is different is the way they are modified to their function. And I also mentioned to you that most of the modifications tend to be in the mucosal layer. So you're going to see how different the mucosal layer of the stomach is relative to other parts, okay? All right. So here we have now our gastric pit. All right? So you can see here that you have your simple columnar cells coming down into the pit. And as they go down, they become specialized, right? You have different types of cells down there. You have chief cells and parietal cells and all sorts of mucus secreting cells, which we'll talk about in a minute, right? So the lamina propria of the stomach is relatively thick, okay? As is the epithelial layer is relatively thick, okay? And then below the mucosa, you're going to have this layer of muscularis mucosa. So it's a thin layer of muscle, which is not enough really to contract the whole stomach, but it can squeeze down on the epithelial layer, right? Then we have our submucosa. Normally, submucosa is filled with glands and nerves and lymphatic vessels, right? So in this case here, now it mentions that the submucosa contains submucosal plexus. And as you know, plexus, of course, are nerves, nerve endings. So when you have a belly ache, this is where the ache is coming from, okay? It is normally the wall of the stomach that you're feeling that ache. And remember, you know, I'm sure everybody can tell the difference between when they feel like they have a burning sensation in the stomach versus they have a belly ache, right? I know the sensation is different. So I'm not saying that when you feel like your stomach a burn, and that is normally occurring in the upper layers, right? When you feel like deep ache, that is coming from the plexus, okay? Then now, below the submucosa, which you can see is not very thick, you're going to have the muscularis externa. And remember, 3 layers of muscle, so it's very muscular, right? Then beyond that, you're going to have your serosa, your outermost layer, which is mostly collagen connective tissue, right? All right. So this is now a look at our pit and the very important cells in this pit. So you have mucous neck cells, right? Now, why are they called mucous neck cells? Because they're near the top, which of course where your neck is, and they're producing lots of alkaline mucus. Then now you have your parietal cells, then your gastric glands, and your chief cells. And all the way near the bottom, you have these cells called enteroendocrine cells, which are sort of delicate, relatively delicate. So you want to keep them as far away from acid as possible, right? So let's talk about what these things do. Now, note here that your parietal cells, chief cells, enteroendocrine cells, again, notice what the chief cell is doing. Notice what the parietal cell here is doing. If you notice what is coming from the parietal cells here. So the parietal cells are involved in the production of hydrochloric acid, right? The chief cells, on the other hand, are involved in the production of pepsinogen. You need both of them, pepsinogen and hydrochloric acid, to form pepsin. And what does pepsin do? Pepsin breaks down proteins, okay? So normally in your stomach, pepsin is floating around in the form of pepsinogen. Remember what I said to you about the ogen? If you see ogen at the end of a word, it normally means it's an enzyme or hormone in its inactive state, right? Now, hopefully, y'all understand why you cannot have pepsin floating around your stomach all the time. Your body is mostly water and protein. Pepsin breaks down protein. So if you have it in your stomach all the time, the pepsin is going to eat away at your stomach lining. So you only turn on the pepsin when you need it. Otherwise, you keep it turned off, right? sorry, mucus secreting cells produce acidic mucus. My apologies. Parietal cells, as I said, secrete hydrochloric acid and an intrinsic factor, which is involved in vitamin reabsorption. Cheap cells produce the pepsinogen. We spoke about how it is activated as well. Now, the enteroendocrine cells here secrete hormones. We have gastrin, histamine, endorphins, serotonin, cholecystokinin. So cholecystokinin, or the CCK, and somatostatin, right? And they're being secreted into the lamina. So we're going to talk about the importance of all of these different substances, right? Now, no surprise, the stomach lining is exposed to the harshest conditions inside your digestive system. That is, of course, because of your hydrochloric acid. Here's the thing. See if this makes sense there. What we tend to find in the animal kingdom, right, is that predators, carnivores, for the most part, have relatively weak stomach acid, right? We have herbivores that tend to have weak stomach acid as well, right? But scavengers, jankro, or coyotes, those tend to have extremely strong stomach acid, right? Now, I'm hoping you all can see why that is. What is the main function of stomach acid? Kills bacteria, activates protein. If you're a herbivore and you're eating lots of plant material, there'll be some amount of bacteria in the plant material, sure. But it is not going to be overwhelming, because mainly the plant material you're consuming is living material. And the living material has its own way of controlling bacteria on its surface, right? So normally when you eat an apple, the only part of the apple you worry about is the surface of the apple. So you wash the apple. Nobody washes the inside of fruits when they cut them, right? And of course, the same thing with a carnivore. When you kill, when a lion kills a wildebeest or something and tears it open, once again, that animal has means of controlling bacteria inside its own flesh for the most part. So inside its flesh is still relatively clean. But of course, since the diet of the carnivore is much higher in protein, it makes sense that the carnivore has stronger stomach acid. What about your junkro? Obviously, scavengers are consuming meat, which is high in protein, and also because it is rotting, it is high in bacterial content as well. So they need very strong stomach acids. Human stomach acid is closer to that of a scavenger, like a junkra or a coyote, than it is to a lion or to let's say a goat. Why is that? It's very simple. Our ancestors evolved as scavengers, right? So you can imagine 50,000 years, 100,000 years ago, maybe more, small bands of humans would roam around the place. When they came across the carcass of some wildebeest the lion had killed, it's a day or two old, but food are food, right? And that is what they'd be supping upon. And because they did it often enough, it forced human beings to evolve a means of reducing the impact of bacteria on our systems. So that is the reason why human stomach acid is so strong in comparison to other animals that are omnivores as well, right? All right. So that, of course, is links right back to why we get heartburn, because our stomach acid is too strong, because our ancestors used to eat a whole heap of rotten meat, basically. And if you think about it, even to this day, we do have taste for rotten foods. Because what is yogurt? It's rotten milk. I mean, what is cheese? That's also rotten milk, right? Think about preserved meat, um, pickled meat, and all of these things. It's basically controlled rotting, right? Dry aged meat. When in the US in particular, not so much in Jamaica, when they kill a cow or something and they cut it up, they don't put it in the freezer. They let it hang for a couple of days in a cold, dry place. Develop what they call that skin, which is basically fungus and bacteria on the outside, which starts breaking down the collagen fibers, and they consider that meat that's some of the best steak you can eat, right? So even to this day, we can see that human beings, our ancestry of loving, you know, not the freshest food in the world still continues, right? Anyway, let's continue. Now, obviously, if the stomach is a very harsh condition and you're constantly at danger of damaging the lining because of the acid, you're going to need that thick coat of bicarbonate mucus. Also, you need your epithelial cells to be as packed tightly as possible to reduce the ability of the acid to get between them and damage the underlying cells, right? Now, it mentions here gastric glands that have cells impermeable to hydrochloric acid. Epithelial cells are packed tight together, so acid can't pass through them. You have a thick layer of mucus over everybody to reduce damage by hydrochloric acid. And when the cells do get damaged, they are quickly replaced. So your stomach is under constant mitosis. Now, we already know the stomach holds the ingested food. We know it is going to do mechanical and chemical digestion. We already know it passes chyme to the small intestine, right? We already know about pepsin. But what about this one here? The intrinsic factor I mentioned earlier with vitamins. The intrinsic factor that is produced by the stomach aids in the absorption of vitamin B12, right? B vitamins are particularly important to pregnant women. So it's very important to you guys, right? So the intrinsic factor produced in the stomach allows you to absorb B12 more easily into your blood. So so once again, there's another example of something being taken from the stomach and being passed directly into your bloodstream. So we had alcohol and we had this, right? Which hopefully will re-emphasize why blood from the stomach has to go to the liver and not straight to your brain. Okay? Apparently somebody pregnant, who knew? Anyway. Now, let's talk about how the stomach regulates its activities, right? It mentions your neural and hormonal mechanisms regulate the release of gastric juice. The idea here is that hormones that are being released by the stomach will trigger the stomach's behavior to change, as well as the activity of your brain will trigger the stomach to change, right? So because of that now, we said that the stimulatory and inhibitory events occur in 3 phases. We have the cephalic phase, we have gastric phase, and we have the intestinal phase. So basically, when it comes to basically eating, consuming food, we do this in 3 phases, okay? Now, obviously, cephalic is head, right? So this has to do with our brain. As it says, this happens before you put food in your mouth. Wait, somebody's actually pregnant? Okay, moving on. Then you have the gastric phase that happens. Gastric, of course, is stomach. Once the food enters the stomach, an intestinal phase is when, of course, food enters the intestines. Are you people serious? Somebody really pregnant or joking at me? Okay, well, congratulations, I assume. Now, cephalic phase. You have excitatory events, which are going to include this. You have sight of the food, thought of food, stimulation of taste or smell receptors. What's going on here? Basically, this is the way advertisements work. Your brain is keyed on food. Remember I said to you earlier that our ancestors evolved in environments where food random. You never know when you'll come across it. So because of that, when you saw food, not only would you have to eat the food, you'd have to feel the desire to consume the food. So because of that, human beings trigger on food by sight. So when you see something that looks nice to eat, all of a sudden you feel the urge to put it in your mouth. This is one of the problems you have with babies, right? There's a reason why babies tend to stick brightly colored things in their mouth because they look like fruit, right? Then, of course, if you're being key to want to put something in your mouth, what else is going to happen? Production of saliva. Because remember, the saliva contains salivary amylase, which helps you to digest that, at least start the digestion of starch. So you look at the food, you know, as I would say in the local parlance, your mouth start to water, right? Preparing you to eat the food. And of course, if you smell the food, that's even worse. Because that triggers the reflex even more. So looking at the food, smelling the food, sometimes you ever just sit down and the thought of food crosses your mind and you realize you're hungry. So just thinking about food can all trigger the cephalic phase, right? Now, there's a reason why when you're watching an advertisement for like KFC or Burger King or one of these places, what do? They show you the food, show you steamer come off of the food, they show people pulling the food open and tearing it, hear them biting down on the food. What are they doing? They're impacting your your primitive mind, which you can't control so easily. Right? They're subverting your will, basically. Right? They're trying to force you into a state of hunger. So you come to them for food. And a lot of those advertisements are very, very effective. Here's another thing that I've noticed that particularly bakeries will do. You ever walk past a bakery and smell the air? Why the air always smells so nice? As they're baking, what I've realized some bakers will do is that when they're baking the bread and other things, they have an oven and the oven has a chimney. The purpose of the chimney is not to take smoke anywhere because everybody's using gas. So what is the oven doing? The oven is taking the air that is rich in baking smells and putting it out into the environment around the bakery. So as you're walking past the bakery and you smell the food, the things are baked, before you know it, you're inside the place, you don't even know how you get in there. All right, and your money's on the counter. Right? So seeing, smelling, all of these things trigger cephalic, right? Now that said, if you can trigger food, there must be a way trigger the desire to eat the food, you must be able to trigger a desire not to eat the food. So that's inhibiting, right? Now, depression is one of these funny things. It's a term that is very overused, right? Melissa, your mic is open. It's a term that is very overused. Generally speaking, depression is feelings of sadness, powerlessness, which occur not for an hour or two, but for weeks at a time. Okay? If you're just sad today and you feel okay tomorrow, you weren't depressed. Right? Now, that said, when you're depressed over a long period of time, in some people, it can suppress your desire to eat. So, somebody has some bad events in their life, and all of a sudden they stop eating for a while. That's depression, right? So once again, your mental state has impacted your ability to consume food, right? Now, that said, for some people, it's the exact opposite. They feel depressed and they eat. Because eating, of course, generates endorphins that make them feel better. So you have the people who wallow in their depression, and you have those who try to counteract it with food. Neither of which, of course, is a winning strategy. Now, notice here it says inhibitory events will decrease in the stimulation of the parasympathetic division. Here's the thing. Your digestive system runs on the parasympathetic system. Pretty much everywhere else in the body, parasympathetic slows things down, but not in the digestive system. Parasympathetic in the digestive system speeds things up, right? Parasympathetic causes the muscles of the digestive tract to move faster, not slower. Causes the stomach to churn more rapidly, not slower, right? So when you consume large amounts of food, you tend to trigger your parasympathetic responses all over the body, which slows down the body in general, but speeds up the digestive system, right? So keep that in mind as you go along. Now, these two hormones here, leptin and ghrelin, are a part of what we call a satiety mechanism. They were discovered in rats that if rats with high levels of leptin in their blood tend to avoid food, and those with high levels of ghrelin tend to want food more, right? So at one point they were trying to produce potentially leptin for commercial use, but there were some side effects that they had to leave it alone, right? Now, you smell the food, you see the food, you hear people talking about the food, now you feel like eating the food. So you eat the food now, food gets into your stomach. That now triggers the gastric phase, right? So what causes the gastric phase to begin? You have the stomach distension, right? So the food comes in, the weight of the food pulls on the stomach wall, that distends the food, therefore, it's in the gastric phase of the trigger, right? And of course, stretch receptors can also be activated neurally. So your brain can send, listen, the leptin supplements, I really wouldn't fool around with them. The reason being is that because there are not very many positive studies on leptin that can be related to humans. The most prominent leptin studies were on rats, right? If you'll notice, leptin is now considered a nutraceutical, not a pharmaceutical. Pharmaceuticals have to go through very rigorous testing procedures to make sure, and let's be honest, sometimes they fail much less. But for the most part, right, they go through these processes to ensure that their danger to the consumer is minimal. And nutraceutical does not have to go through any of that. And so you'll find a whole heap of nutraceuticals on Amazon. And if you read the bottle, at some point, they will tell you that they're not responsible that anything happens to you. And at some point in the fine print, it will tell you that your consumption of this item, if anything goes wrong, it is not their fault. You can't sue them, right? Whereas you can sue a pharmaceutical company. So please be careful with nutraceuticals, all right? Even the production of the nutraceuticals, the quality of them will vary. So be very careful. Anyway, so chemoreceptors. It mentions here the activation of chemoreceptors by peptides. So you eat the food has proteins in there, peptides, right? And that also triggers the gastric phase. Weird enough, caffeine will also trigger the gastric phase. So coffee in the morning, right? And rising pH. Why does the pH rise? Because the food you're consuming has a higher pH than the pH of the stomach. So the pH in the stomach is going to rise, right? You can even have the release of gastrin, a hormone in the blood. All of these are going to trigger the activity in the gastric phase, okay? Then now you have the inhibitory events, things that once again can slow down the gastric phase. Believe it or not, if your stomach is too acidic, it can trigger inhibition of the gastric phase. If your stomach is much more acidic than it should be, during the gastric phase, you produce hydrochloric acid. So if your stomach is already acidic, the last thing you want to do is make more acid and put in there. Because remember, your stomach wall is not immune to the acidity. If your pH gets too low, you'll eat right through the mucus and start eating through your stomach wall. So it makes sense that if the pH gets too low, your stomach does not want to make more hydrochloric acid, right? Also in here, emotional upset overrides the parasympathetic division. So simply put, if you're agitated, you tend not to be hungry. Now, here's the thing with chewing bubblegum. Bubblegum is sweet, right? And you are swallowing saliva, and that saliva contains carbohydrates, but doesn't contain a lot of protein. It doesn't contain a lot of, well, it doesn't even contain a lot of carbohydrates, right? But here's the thing. It triggers the gastric phase. I'm sorry, it doesn't, it triggers cephalic activity in your brain because of the taste and sometimes the smell of it. So it is more responsible for making you want to eat, right? So it's not really doing much for the gastric phase per se. But the cephalic phase, definitely bubblegum, chewing gum, whatever you want to call it, will make you hungry, right? Now, once again, if you're upset, you tend not to want to be eating at that point. You know, gunman are running down, the last thing you're thinking about is a hamburger, that kind of thing, right? So emotional upset can override the parasympathetic division. So if you're actually stressed, a lot of times, and once again, stress is what the way I say stress is not the same as maybe what you're thinking of. When people say they're stressed, stress is not something that you can have for like days or weeks at a time. Stress is in the moment, something is happening, your mind needs to be focused on it right now. You're walking down the road, a bad dog jumped the fence, right, that's your stress. Right? Your boyfriend left you, that is not stress. Right? You might get depressed over that, but you're not stressed. Exam coming up, you're not stressed. Right? You might be stressed doing the exam. Right? That is because that is when the stimulus is on you, which is much different from the way we use stress, right? Stress is short term. Stress is not something that is going to be on you for weeks and months at a time. You might want to say it's depression or whatever, but it ain't stress, okay? Because stress, remember, stress is involving the release of hormones, etc., etc., fight or flight. Nobody's in a fight or flight state for weeks and months at a time. Okay. Just keep that in mind, right? So anyway, so all of these things we mentioned before will inhibit the gastric phase. So what does this mean? It means food will come into the stomach. Food is supposed to be churning up. Food is supposed to be mixing with the gastric juices to form chyme. So if you're inhibiting the gastric phase, you're reducing the ability of these things to happen, which of course means you reduce the rate at which food or the chyme is moved into your small intestine. So if your stomach is too acidic, food sits in the stomach for longer. If you're upset, food sits in the stomach for longer, right? But of course, if you're nice and relaxed and all is well with the world, you digest the food faster, right? Now, intestinal phase. So now this moving into the intestines now, you can't call it food anymore, you call it chyme, acidic chyme, right? because it is the crushed up food mixed with the digestive enzyme, the pepsin, and the hydrochloric acid. So you've now formed a mush, a very watery mush, right? Almost like porridge. So in the intestinal phase, once the chyme comes in, because it is acidic, it is going to cause the pH of the stomach to drop, right? And this encourages, as it says here, the gland activity. Then inhibition, distension of the duodenum. Basically, the idea here is that when partially digested food, remember it's coming from the stomach, so this chyme comes into the small intestine. The acidity of that chyme triggers the release of enzymes and other substances onto the food. So you can start breaking it down, right? But the very presence of a lot of this chyme in the small intestine prevents more chyme from being pushed in on it. Does it make sense to you? When your stomach, let's use this, when your stomach squirts food, I keep saying food, let's call it chyme, squirts chyme into the duodenum, the duodenum needs time to start acting on that chyme, okay? It needs a moment. So once you have a lot of chyme in here, the weight of the chyme suppresses the stomach activity here. So more chyme isn't pushed forward to displace what's there. When the chyme that is here in the duodenum starts moving down from the duodenum, and you get less now here, that is when now you activate and allow more to get pushed in. So remember I said here that the stomach isn't just leaking out the chyme continuously. It's essentially squirting out, right? So it's one squirt, you fill up here, starts to break down, starts running down the duodenum, you get less here, another squirt comes in. The weight tag once again stops the stomach from squirting anymore for a while. You start breaking it down again, then moving along, then another squirt comes in, right? Keep that in mind. Then now inhibitory phase, remember, that's the distension of the duodenum. Also, the presence of fatty, acidic, or hypertonic chyme. If there is a lot of fat in the chyme, it slows down the emptying of your digestive, of your stomach. So fatty food takes longer to digest. Now, this is one of the reasons why, for example, back in the day, well, I mean, I shouldn't say back in the day, still have people who do it. In lots of countries, all right, think about what we in Jamaica normally have for breakfast. And I'm not talking about like porridge and those things, right? Because, I mean, we eat a lot of protein and fats. Look at ackee and saltfish. What is ackee and saltfish? Ackee and saltfish is protein and fat, right? And then you have sausages and eggs and all of these things. These things tend to be high in fat and protein because fats and proteins take longer to digest than carbohydrates, right? So you eat a meal, a nice big meal full of eggs and sausages or ackee and saltfish and these kind of things. It sits in your stomach for longer because it requires more time to digest. So therefore, if you eat a nice big breakfast with these things and then you go to work, you can work for hours and hours and hours before you start to feel hungry again. Versus cornflakes. Cornflakes is like one of the worst things you can have for breakfast. Cornflakes is mostly made up of um uh, a mixture of simple sugars and starch, both of which are relatively easy to digest. Right? When was the last time you had a bowl of cornflakes and your belly was still full 6 hours later? Right? That's what I'm saying to you. Cornflakes blow right through your system. It's a waste of time and money. Right? Same thing with cornmeal porridge. People always talk about, oh, cornmeal porridge. Cornmeal porridge is not as bad because that's larger chunks of ground corn, so that you might stay full a little longer, but it is still nowhere as good as a plate of sausage. Anyway, let's understand it is the fat and the
Sir,
protein.
what about granola?
Granola. I'm not a goat. What am I eating that for?
Yeah.
That's a goat food. Granola is one of these things that actually is here's the problem with granola. A lot of the grains in the granola are indigestible. They're full of a fiber, which means your body can't do nothing with them. So you just pass them through, right?
Sister, what about the cornflakes, like the wheat ones with the raisins, not the normal ones?
What difference does that make? It's still cornflakes. Why we have some cornflakes enthusiasts in here fighting it. I'm sorry, but at the end of the day, cornflakes is not particularly good for you. If you have to choose between a bowl of cornflakes and a bowl of cornmeal porridge and some crackers, take the crackers and cornmeal. At least you'll
Sir,
stay
cornmeal
fuller for
porridge
longer.
not last long.
Hmm?
This cornmeal porridge not last for long.
Neither does the cornflakes. But generally speaking, the cornflakes, especially the frosted ones, the sugar content is way higher than the cornmeal porridge. Unless your hand very excessive when you pour the milk. Right? Honestly, I spent many years eating cornflakes too, so I can't say anything to you. These days, my go-to breakfast meal is actually liver and fried dumpling, which is what I should have had this morning, but never got a chance to get it. Anyway.
Sir, too much fried dumpling.
I know I really should be eating because once again the problem with the fried dumpling is that it is carbohydrates and processed flour. It's easier to digest than say if I had some sweet potato or something like that would have been better. But liver and sweet potato, no, thank you. Anyway, so if you're trying to consume something that will hold you for the day, it has to be high in fats and proteins. And you can see why. When you have lots of proteins, you have to inhibit the gastric phase, intestinal phase, to give the protein time to break down in the stomach using the pepsin. If you have lots of fat in the meal as well, you have to inhibit the intestinal phase to allow for the breakdown of the fats. Remember, one of the things that has to happen when you're breaking down fats is that you have to release bile into your duodenum, right? So bile salts have to go in here and emulsify the fat, and then lipase has to break it down, and it takes much longer. As I said to you, the easiest thing to break down are carbohydrates. So anything you consume that is very high in carbohydrates will not last long in you, right? Anyway. Now it mentions here that we have here intestinal phase. You have initiates inhibition of local reflexes and vagal nuclei. What does this mean? It means here that this is what the fat and the proteins are doing. By inhibiting local reflexes, and the vagus nerve, as you know, it goes to the intestines. It reduces the rate at which the muscles of the stomach contract and squeeze the food, the chyme out. Closes the pyloric sphincter. This, of course, is how the chyme gets into the small intestine. So if you close that, you can't get the chyme in. Releases enterogastrones, which inhibit gastric secretions. So you're reducing the production of stomach acid as well, right? All of these reduce the rate at which chyme moves into your duodenum, which means, once again, the food sits in there longer. So nice greasy breakfast lasts you longer than a bowl of cornflakes, right? And high fiber food does not there's not a lot of is there okay. Granola, as you mentioned, is high in fiber. The problem with very, very high fiber food is that you cannot digest most of it. So when your stomach realizes it can't do that, it simply passes it through. So high fiber tends to go through you much more quickly than even your normal carbohydrates, your starch, right? Because you can't do anything with it. So you need to make space for something that you can do with, right? Somebody mentioned this thing about color.
Sure.
Yes.
So yes, it is high in fiber, but is it the fiber good to help clean the colon?
Sure, but we're talking about nutrition now, right? And how fast the stomach empties. We're not talking about the colon or anything like that. Obviously, there are reasons to consume high fiber foods. What I'm saying to you in terms of stomach emptying, your stomach empties very fast on fiber, right? Because your body really doesn't need to process very much of it, because there's not very a lot in there your body can do anything with. But yes, it is important for peristalsis for sure. Now, the kill you faster business. It is so fascinating that in the last few years, we've come across, our scientists have done many a large study that have now debunked this cholesterol idea. I mentioned it to you in class last week that the normal cholesterol that you're getting from meat seems to have very negligible impact on the formation of plaque. It seems more and more that it is plant-based cholesterol that cause most of the problems, not the animal-based one. Interesting idea, right? Anyway, so this slide here simply summarizes what is going on in each of the phases, right? So please make sure you give this one a review, right? Now this here now, so this is activation and this is inhibition. So both of these slides, please make sure you give them a go through, right? Now, hydrochloric acid, the actual stomach acid production. It mentions here HCl secretion is stimulated by acetylcholine, histamine, and gastrin through a secondary messenger system. Okay, so these things are released, and then they cause now the activities that result in release of hydrochloric acid. So they themselves do not directly cause it, right? That's why it's a second messenger system, right? It's like somebody tell you the boss tell you to tell somebody something, right? That kind of thing. So the boss tells you to do something, that James must do something, and then you give the message to James. So you're the second messenger, right? All right, release of hydrochloric acid is low if only one ligand binds to parietal cells. It's high if all three ligands bind parietal cells. What this is saying is that when you have histamine, gastrin, and acetylcholine all interacting with the parietal cells, you're going to produce more hydrochloric acid, right? Because if you're being, think of it this way. You know, when you're young, your mother tells you to do something, the director soon come to. No, let's say your older relative, your brother tell you to do something, you'll get to it. Your mother tell you to do something, it seems slightly more important. Your father come and say, look here, all of a sudden, it's a very important task. So the more people telling you to do the same thing, the more likely you are to do it, right? So the more of these you have all stimulating your parietal cells at the same time, the more likely the parietal cells are to release hydrochloric acid. So the ACH is saying do it, histamine is saying do it, and the gastrin are all they're saying do it. Parietal cells are going to do it, right? Now it says that antihistamines block proton hydrogen receptors, and this decreases the release of hydrochloric acid. So antihistamines can decrease your stomach acid production. So people who have allergies, who are constantly living on antihistamines, you might find the stomach pH rises, which means that you're more likely to get stomach infections and things like that if you live on antihistamines, right? All right, follow me now. Here we have gastrin, acetylcholine, and histamine. This is the stomach wall here. Okay, this is where this out here this is where the serosa is. You have them binding to the receptors on the stomach wall and then causing the release of these here. These are the second messengers. Okay? So the gastrin and the ACTH and histamine are the boss, right? And then these are the workers telling this person what to do. So the more of these you have binding, the more of these second messengers you get produced. Then these second messengers activate this protein here called kinase, right? Then kinase is going to activate the proton potassium ATPase. You can say ASE, that means it's an enzyme, right? Then you have protons, H plus, being pumped into the stomach. At the same time, potassium is being pumped into the stomach lining. So this is in the lumen. This is within the stomach itself, okay? Now, while that is going on, over here, you can see carbon dioxide is being absorbed into the stomach wall. Now, this should look familiar to you. Combined with water, you get carbonic anhydrase. Carbonic anhydrase, sorry, is going to combine them with water to give you your dihydrogen carbonate. Then this breaks down to give you bicarbonate, and then the protons that you'll be pumping into the lumen. That's where they come from, right? So HCl, they need. So here we have H, now we need the Cl. Now the bicarbonate is pumped out of the stomach into the blood vessels of the stomach, right? So that now means that the blood leaving the stomach is filled with bicarbonate ions, which of course make it alkaline, hence an alkaline tide. And while you're pumping out the bicarbonates using bicarbonate chloride antiporter, as you're pumping out the bicarbonates, you're pumping chloride ions from the blood into the stomach lumen. So now we have the H, we have the Cl, and of course, they combine, you now have hydrochloric acid. All right. Does that make sense? Any questions? Are we good? One more time. What should I do?
One more time, sir.
All right. One more time. So remember now, this here is the serosa. Serosa. Okay. So in the wall of it now, you have the receptors for gastrin, acetylcholine, and histamine. When they bind to their receptors, they cause the release of the second messengers. In this case here, we have calcium for gastrin and acetylcholine, and we have cyclic AMP for histamine, right? So these second messengers here now bind to the protein called kinase. Kinase, of course, is an enzyme, and they activate kinase. Kinase then activates the proton potassium pump, okay? Which is different from the sodium potassium pump, right? The proton potassium pump is the pump potassium into the stomach wall, right? And then pump protons into the lumen. So now you're filling the lumen with H plus, right? Now, of course, we don't want H plus, we want HCl. Now, but let's talk about where the H comes from in the first place. You can see here, carbon dioxide is moving into the stomach wall, combining with water, using carbonic anhydrase, form H2CO3, which breaks down, remember, from circulatory system, or the respiration, into protons, which is what we want, So you pump that into the lumen. You also get bicarbonates, right? The bicarbonate now is going to be pumped out into the blood vessels, leaving the kidney, the stomach, making that blood alkaline, hence alkaline tide. While that is happening, the same protein that is doing the pump, which is the antiporter here, is pumping chloride ions from the blood into the lumen. So now we have protons and we have chloride both in the lumen at the same time. And of course, a positive charge and a negative charge come together, you now have your HCl, right? So they both come together to give you the hydrochloric acid. All right. And that is how hydrochloric acid is produced, okay? So it actually means that after you eat food, eat a large meal, your blood pH might increase a little bit because of the alkaline tide. So your blood becomes more alkaline as your stomach becomes more acidic, right? Okay. Now, it mentions here the stomach pressure remains constant until about 1 liter of food is ingested. So once you have enough food to take up about 1 liter of space, it is going to cause relaxation to occur, right? So it's relatively unchanging pressure results from reflex-mediated relaxation and plasticity. All it is saying here is that the stomach can stretch enough to hold a 1 liter without much of a problem, right? That's where the plasticity comes in, right? Then now, reflex-mediated events now. So you're gonna, as I said, recessive relaxation as food travels in the esophagus. So as you're swallowing the food and the food is moving down the esophagus, the stomach knows the food is coming. So the stomach starts to relax, right? It's already starting to get ready to receive that food. Then it mentions here adaptive relaxation. Basically, as more and more food enters the stomach, the weight of the food triggers the stomach once again to relax even more, to stretch out, right? So reflex-mediated events, they swallow the food, stomach knows the food is coming, starts to relax. Stomach that's receptive. Adaptive, this food in the stomach, is enough food to start putting pressure on the stomach wall, stomach starts to relax, right? As I mentioned here, the plasticity is the intrinsic ability of smooth muscles to exhibit stress relaxation response. Basically, all it is saying is that as you put pressure on the stomach wall, the stomach muscles will relax and stretch out. That's it, you know? All right. Then now, we have gastric contractile activity. Now, obviously, the food has to be mixed up and churned up to form a chyme, but you also need to be able to move that chyme out, right? So it mentions here, peristaltic waves moves towards the pylorus at a rate of 3 per minute. All it is saying is that every 20 seconds or so, a wave of contraction moves from the fundus region and waves down towards the pyloric region. And it helps to push the food down towards the pyloric region, right? So every 20 seconds or so, this happens while there's food in the stomach. So in the upper part of the stomach, the body now, the food is churning up and mixing with the digestive juices. And then every 20 seconds, you're pushing that stuff further down towards the pyloric region, right? It mentions here that this 3 per minute rhythm is controlled by your basic electric rhythm cells is initiated by pacemaker cells called your cajules. So just so you had sinoatrial node, the stomach has these cells called the cajole that do the same thing. Okay? Now, as it says, the most vigorous peristalsis and mixing occurs near the pylorus. So this is now where you're finishing off the mixture to make a chyme. You're squeezing out any chunks that are left here. So it makes sense that near the pyloric region, where you're getting the chyme ready to squirt out of the stomach, you do your final mixing up, right? And then, of course, as we know, the chyme is squirted out of the stomach into the duodenum, right? Then you it holds off a little until the duodenal chyme is dealt with, and more will be squirted in, right? So that's why it says here, chyme is either delivered in small amounts to the duodenum or forced backwards into the stomach for further mixing. So if there's lots and lots of protein in the chyme, right? And the chyme comes in and there's still lots and lots of proteins. Remember, I said proteins, I didn't say peptides or anything like that. Then you can push the chyme back into the stomach to continue digesting the proteins before you let it back through again. Which also means, once again, that high protein takes longer to digest than carbohydrates, right? So food stays in the stomach longer again. So remember now, hopefully it makes sense to you that I've explained why high fat food take longer to digest and why high protein food takes longer to digest. You'll notice that there's no such nothing like this goes for your carbohydrates. Carbohydrates just blow right through, right? Now, this is just showing you here the chyme being squirted out into the duodenum in small concentration, right? Now, it mentions here that gastric emptying is regulated by the neural enterogastric reflex. Neural, of course, brain, enterogastric, inside the stomach. It mentions here that the hormone enterogastrone is going to be involved in triggering this now. And it says duodenal filling inhibits gastric secretion. I mentioned already that once the duodenum starts to fill with the chyme, you need time to process it. So once the duodenum is heavy with chyme, it inhibits stomach from contracting and pushing more chyme in, right? Notice carbohydrate-rich chyme quickly moves through the duodenum. So when you sit down and you decide to have cake for lunch, within 45 minutes, it's like you didn't eat anything, right? I'm sure everybody in here has had some a cake or a sugar bun or something and say, oh, that's lunch. And like half an hour later, you're like, boy, did I eat anything? That's crazy. What happened? That is because carbohydrates rich chyme blows right through the system. Because most of the digestion of carbohydrates occurs in the small intestine. There's no reason to keep it in the stomach. And not just in the small intestine, in the lower part of the small intestine. So no, if you want a feeding lunch, it cannot be very, very high in carbohydrates. It is not going to cut it. Even bun and cheese. The one thing that saves bun and cheese are the cheese. Right? Now we have the fat-laden chyme, of course, is digested more slowly because it has to stay in the stomach longer because it takes longer to break down the fatty acid, break the fats down in the duodenum. Right? As I said to you, you have to mix it with the bile salts and emulsify the fat, and then you move in the lipase to break it down. It takes more time. So therefore, you have to hold the chyme there longer, right? So this lovely diagram here now shows you the impact of specific hormones on stomach contractility. So please make sure you go through this one, right? So it mentions here the duodenal enteroendocrine cells are releasing CCK and the enterogastrones here. And enterogastrones, as it says, the contractile force and rate of stomach emptying decline. So they slow down the rate at which the stomach is emptying. And this is, of course, going to be most important, once again, for food that is high in fat and proteins. Food high in carbohydrates, you're not going to release a lot of these, okay? So please go through this one again to make sure everything is well. Now, small intestines. Let's talk about the basic structure of the small intestine now, right? Now, as it says here, it runs from the pyloric sphincter to your ileocecal valve. Ileo, as in ileum, and cecal, as in cecum, right? It's just telling you where the valve is. That's three parts. The duodenum, where most of your enzyme digestion is going on. The jejunum, where most of your absorption is going on. And if your ileum, which is a shorter section, some absorption occurs here as well, quite a bit. Right? And then now you pass on what is left into your cecum from here. So the jejunum and the ileum are the two places where most absorption occur, right? Now you also have accessory organs involved. Remember, accessory ones are the ones that chime, food, whatever you want to call it, does not pass directly through, but they contribute substances towards digestion, right? So bile duct and bile, of course, coming from your well, the bile, of course, comes from the gallbladder. And remember now, the liver makes the bile, stored in the gallbladder, right? And then released into your duodenum. You also have the pancreatic duct, which takes pancreatic secretions from the pancreas, obviously, also brings them to your duodenum, right? And both of these ducts are going to join together to form something called the hepatopancreatic ampulla. And therefore, bile and pancreatic juice, which is, of course, a mixture of enzymes and bicarbonate solution, and the bile all enter your small intestine through this one little area called the hepatopancreatic ampulla, right? So both these organs are dumping from the same port. And the opening and closing of this port is controlled by something called the sphincter of Oddi, right? Now, obviously, I'm hoping you realize that if so a gallstone or can potentially block this sphincter. Well, not kidney stones. So when a stone blocks now the hepatopancreatic ampulla, can cause all kinds of problems, which we'll talk about a little bit, right? Just keep that in mind, because sometimes people think gallstones are not a big deal. Minor inconvenience, they can be really, really bad. Now, it mentions that the jejunum extends from the duodenum, some people say duodenum, to the ileum, right? And the ileum joins the large intestine at the ileocecal valve. All right. So remember, this is just our basic anatomy we're looking at. Now, it mentions here the small intestine has some modifications to it to increase surface area. Remember, what is the primary purpose of your small intestine? It is there to complete digestion as well as to do the absorption. So in both cases, you need large surface areas, right? So you have these structures called plica circularis, and they're folds, circular folds in the mucosa and submucosa. Of course, as we know, folding increases surface area, right? Then you have the villi. Everybody know villi from CSEC. And then there's finger-like extensions of the mucosa. And then on the villi now you have the microvilli, which are tiny little extensions from the cells themselves of the villi, all of which increase surface area for absorption, right? All right. So here we have our duodenum. Okay. Here's our jejunum down here. Here we have our gallbladder. And then you can see here now, the gallbladder releases now bile into a cystic duct here. Then the cystic duct merges with a common hepatic duct here. And then we end up now with a bile duct heading towards the intestines, right? At the same time, you have the pancreas here. You can see the pancreas is nestled right here in the duodenum. And the pancreatic duct, the main pancreatic duct here, is also heading towards the intestines. And then the bile duct and the pancreatic duct merge here at the ampulla, right? Then the sphincter of Oddi will open to allow the secretions to enter the duodenum. Now you can imagine a gallstone forming here and making its way down because it's small enough all the way down here and just blocking the ampulla. Now this is a serious problem because now you have the pancreatic juice that should be flowing into your intestines can't reach anymore, which all of a sudden it means that you can't digest proteins, carbohydrates, lipids properly. Then now also the bile that you need to emulsify the fat is not getting through anymore. So if you're suffering from this condition, your feces all of a sudden becomes very watery, very greasy, smell even worse than feces normally do, because you're not able to break down the feces properly and absorb nutrients from the feces. So this food, this chyme, moves now into your large intestine, and it is very, very rich in nutrients. And the bacteria in your lower intestines love this very, very nutrient-rich chyme and start working on it. So you find plenty of gas being released from you as well, very bad smelling gas, right? Causing bloating and you feel sick. So you're producing very, very greasy, watery feces, and you're bloated and sick all the time. And in addition to that, of course, there's a backup of fluid in your pancreas. So you can get pancreatitis too. So your pancreas becomes inflamed, all of which can be caused by one little gallstone right here. Okay? It is something that happens. All right. Now, let's move on. This is a diagram I'm sure you've seen at high school. Okay? What do we have here? We have the villus. And when you look at the cells of the villus, you see little microvilli on them. Right? Now, as we know from C6 as well, within the villus now, we have capillaries and we have the lacteal. For most of it, this would have been the first time you'd have seen anything about the lymphatic system. Right? Now, as you hopefully remember from CSEC, when you break down proteins into amino acids, most of these amino acids go from the lumen, pass through the cells. Remember, these are mostly simple columnar cells, and pass right into the capillary inside this this villus. Okay, and the same thing happens to the carbohydrates. Carbohydrates broken down into glucose, and other monomers, but mostly glucose. And then this is passed once again through your cells and then passed on to your capillaries. So amino acids, glucose, straight into the blood, no problem. Whereas, of course, fatty acids and glycerol cannot go straight into the blood, as you know. So they have to go first into the lacteals here and then pass through your lymphatic system before they finally get to the blood. And up here now, this is showing the folds here, right? The plica circularis. And of course, if you're folding like this, you're once again increasing surface area, okay? All right. Now, the it mentions the epithelium of the mucosa is made up of absorptive cells and goblet cells. Obviously, goblet cells, remember, make mucus. Absorptive cells, I mean, just from the name, you should know what they do. They're absorptive cells, they must be absorbing something, right? We also have enteroendocrine cells. And endocrine has, of course, hormones, right? And they're also interspersed with T cells called intraepithelial cells, right? Intraepithelial lymphocytes, sorry. And of course, you know what lymphocytes are for already, right? And here it goes. It says they release cytokines upon entering and encountering antigens. Okay. So floating around, moving around inside your intestines, you have white blood cells. They're looking for antigenic molecules. They're coming into contact with anything strange, they release cytokines. Cytokines will basically trigger multiple things, right? One of the things that they can trigger is the activation of other white blood cells. And them plus other factors will lead to things like diarrhea and stuff like that to counter potential bacteria in your intestines, right? All right. Now, this is slide 61 of 100. We need to finish today. So here's what we're going to do. I am proposing that we take, let's say, 30 minutes break and come back at 4:15 and finish up the last 40 slides. All right? Any objections there? Take 30 minutes and come back?
Sir, why we have to take such a long break?
You want to take 15 instead? It's up to you now.
30 minutes, sir. 10 minutes.
What, 15 minutes and come back? We only have about 39 slides left, so that's probably about an hour. So you want to take 15 minutes, refresh and come back? What's the decision?
Yes, sir, that sounds okay.
All right, so we'll come back at 4 and then we'll finish this up. All right, folks? So, which is good because I need time for this video to process. All right, folks, come back in 15 minutes. So that's 4 o'clock-ish. Or 4:05, whatever it is, 4:05.